So in this work, basically what we're doing is working with, first of all, I'm Chris Williams, working with Tom and Kathy Liu on this project, which basically is to take the work that's being done with Olga and Tom at the Lens Lab. So they're synthesizing all these quantum dots. So they're doing sort of the materials development side, and so we're doing the other half, the manufacturing side. And it's really specifically focused on this idea of those quantum dots, right? So these quantum dots, these things that have one color in visible light, but they fluoresce at a different color under UV light. So why should we care about that? Well, Tom and I and Olga and Amy, the PhD student who's also working on this, sort of sat down and thought about where this would be useful. And what we really ultimately came up with was that there's a lot of potential for counterfeiting with additive manufacturing. With 3D scanning, you can basically replicate any part. And so there's an opportunity, so that actually is sort of driving some people away, especially Tom and I have given several talks up in DC, and they're sort of afraid of what could happen, right? Do we have to change our IP laws? Do we have to change the way in which products are developed? Should we outlaw 3D printing, right? So Tom and I have put forth the point, which is, no, what you do is you take advantage of what 3D printing does best, which is selectively place materials where you want them. And so this technology allows us to actually tag our parts as they're being fabricated, which prevents other people from being able to reproduce the objects that we print. So yeah, you might be able to 3D scan the object that we create, but you will not be able to detect the embedded tagging that we've done. So this could have multiple effects, both on just any industrial part, but even to 3D printed weaponry, or even certification of parts, which is another opportunity. So with that in mind, we take a look at Tom's and Olga's quantum dots. So how do you put them into the 3D printing process? That is definitely not trivial. So basically the idea is this beautiful equation that Amy put forth, right? Additive manufacturing plus quantum dots equals profit. No, what we call a physical unclonable function, actually. This is something that Tom has prior worked with his colleagues in Germany, which is a physical cryptography. It's something that in the manufacturing process, the actual deposition of those quantum dots is completely stochastic. So we ourselves, as the manufacturers, cannot even reproduce that same deposition pattern. So we can, at the micro scale, reproduce the same deposition pattern, but on the nano scale, we have no control over where those droplets go, which therefore provides us a unique identifier to the products that are being manufactured, which is the key to all cryptography. And again, this is something that Tom has done prior work in. So how does this work? Well, what we chose first was we have several additive manufacturing technologies in the Dreams Lab, and we chose the one commercial technology that allows us to do functionally graded materials or mixed materials. So this is actually an inkjet printing process, and in this inkjet printing process, there are 3 different types of inkjet heads, and those inkjet heads can deposit 3 materials simultaneously. Fundamentally, it's a photopolymer, so it's a liquid resin that cures solid when exposed to UV light. So what you're seeing actually is the printing block, an animation that my student Amy put together. So this printing block goes back and forth over the part, and these UV lights actually are immediately curing, solidifying that resin, and this elevator moves in the Z direction. So we build layer by layer from the bottom up. So the idea, of course, is to introduce quantum dots into the existing ink, and then, again, we could selectively place those quantum dots wherever we like. So that would then allow us to tag parts. So what this big test funding really supported was the science, not only the science of the creation of quantum dots, but really what it really focused on was the science of the manufacturing process. Because as soon as you start putting nanoparticles into ink, bad things happen, especially when it comes to when you want to inkjet parts, right? So we looked at rheology, so surface tension, viscosity. We looked at the jetting characteristics. We looked at the curing. And we are developing the first models of quantum dots for these types of characteristics in the context of additive manufacturing. We also looked at the effects of the particles on surface finish. So we'll talk a little bit about that. So Tom and Olga generated multiple concentrations of quantum dots, which then allow us to study surface tension effects and also allow us to study viscosity effects. The gray bar there is the control sample. So we're doing really fun, small concentrations, primarily because that's actually all we need to get the visibility that's required. So this is naked eye visibility, meaning at 0.5%, I can actually, with my naked eye, see the quantum dots fluoresce. So we also did some calculations, some theoretical calculations about jetting. This is called the Onizorg number that shows us that with these variables, even at the highest concentrations, we were able to still jet. We also looked at curing. So this is a photo curing technique. And quantum dots fluoresce in the UV light. So we have to be concerned about how they change, how much or how well this polymer cures. And again, that's something that we are just now finishing up modeling, actually, again, developing a curing model, and that's the key piece of additive manufacturing, is helping develop the process parameters to tune my machine to give enough energy to cure my polymer to get the right layer thickness that I need. The other thing that we used the funding for was to purchase a custom inkjet test stand station. So before we throw this specialized ink into our $350,000 printer, we actually purchased a test stand. So with that, that's a single inkjet nozzle that has the same diameter of the printer itself. We have a CCD camera with a strobe on the other end here. And we also have a heated reservoir, so we can heat the polymer up to the temperature at which it's printed. We can also print solder with this machine. It's a wonderful piece of technology. And what it allows us also to do is actually image individual droplets as being jetted, so we can actually study the effects of all the polymers. Right? On the bottom right, what you see is an image from a journal article that was published with Tom and Olga, which shows how this is individual inkjet droplets, and then under visible light, and then under UV light with a fluorescent microscope, showing that these taggants are actually still working, and most importantly, they're not dispersing to the edges of the droplet. So we verified now that this can be jetted, and now the next step is to synthesize lots and lots of quantum dots to load them in our commercial machine. But this is a really nice piece of technology. This is going to allow us to really make some major headway in the inkjet printing world with additive, not just for this technology, but any other kind of novel material system that our colleagues want to experiment with. As Tom showed, I brought the pieces you can hold in your hand there. As he was saying, we actually developed a way to embed these. Right now, this was done manually, but next step is to actually directly jet them, and it's shown that they can fluoresce. We've actually been working on what we call the invisible ink. So this is a very high concentration, 2%. If we work in this sort of 0.2% range, it's very difficult to actually see the quantum dots in visible light, so you can almost print in an invisible ink, and then you would only see it when exposed to UV light. We've done some studies of surface finish, different post-processing steps, polishing and whatnot, to actually see how that affects visible, the naked eye visibility, as well as some other kind of surface finish. But finally, basically, in summary, what we've really done here is, together with Tom and Olga at the Lens Lab, with their providing us materials, together we were able to create, again, as Tom mentioned, those first embedded quantum dot nanocomposite parts in a 3D printed shape. And we really advanced the science on the inkjetting and embedding and curing models. And that's actually the subject of a PhD student's dissertation, which will be defended in July. So, quad chart, you have lots of overflow slides. I guess really what I want to highlight here is this NSF Career Award actually is all about printing copper, but that's, so it was not necessarily related to this, but the back end of that award was all about jetting nano copper and nano carbonaceous material. And so all the work that we did with, Amy and I did about the jetting pieces fed directly into that. That's what really, obviously it's a completely different material system, completely different set of steps. But the modeling, that knowledge, we were able to show that we could do this, really, I think, helped the proposal out quite a bit. So I think I would definitely connect that award to this program of all. Some other nice awards and other recognitions. Really good collaborations, though, as Tom mentioned, with MakerBot, but as well with the company Objet itself, and some other companies that have expressed interest in licensing this IP that we continue to work towards. So with that, I guess I'll close and answer any questions.